Great. Good afternoon, everyone. I'm Brian O'Kelly, CEO and co-founder of AppNexus. I'm so excited that you've all joined us here at Optimize today. Now, as most of you know, I started my career in the industry at a little company called Bright Media, where I was the Chief Technology Officer. And I stumbled upon the idea of the ad exchange while trying to figure out how to effectively distribute the computing of the Bright Media platform out not just to other data centers, but to other geographies. As it turns out, there's an arbitrage opportunity, which of course our friends figured out how to take advantage of, and the ad exchange was born. And tomorrow, for those of you who will be attending or watching the summit, I'll be talking a bit more about the evolution of exchanges and marketplaces. But today is really all about technology. So I want to talk about a major technological problem with Bright Media that has brought us here 10 years later to this room. And that problem is that Bright Media was a closed platform. Yes, we tried to build APIs on the end of it, and there were one or two people out there who figured out how to use those APIs. But what our clients really wanted to do was to find ways to extend the platform to do more, to bring their own algorithmic logic into that real-time decision that we were trying to make. And it wasn't possible. We tried. There's actually one Silicon Valley startup that actually built a dynamic module that you could compile into the Bright Media platform. And if everything worked well, it would run real-time executable code. It would call out for some cache libraries. It was this incredible Rube Goldbergian device. And immediately upon turning it on, I believe it crashed every single server, and we said, never again will we do anything with dynamic modules, and we will never again try to do any kind of insertion of real-time decisioning code into our production systems. And that was that. And then, a few months ago, I was telling this story and sharing this experience with some folks in our office and said, I can't believe it's 10 years later and we still haven't figured out a better way to run custom algorithms than to force people to build these big, complex, fragile bidder stacks. And you'll see later, if you attend Andrew Sweeney's talk, people aren't all that good at building bidders. We know this because we can see the timeout rates, and we can see the percentage of our traffic that these bidders handle. And so we believe there's a huge amount of inefficiency still out there because of how much traffic bidders simply can't buy. And don't get me started on error rates, 50% in many cases. That means that a very small percentage of ads that are available to be auctioned are actually being successfully bid upon by all of the real-time bidders out there. And if you look at our platform, our engineering team, of course, has the advantage of being in the same data center. So we don't have to worry about latency. What we do have to worry about is the incredible volumes and the technical complexity of trying to put real-time bids against huge volumes of real-time traffic. And so perhaps today, in 2015, we could find a better way to try again, to create, if you go to my little slide, I don't have a clicker. Clicker. There we go. This was also invented in 2015. How big this is. It's the size of a cell phone. It's great. I didn't even click it. Telepathic clicking. It's pretty cool. And so while this Pat trying to plug something into Bright Media there, it isn't how plugging works. Can we solve this problem today? And just as a number, aside from the timeout rates and the error rates, we did some math and talked to a number of people who've either built their own bidder platforms or who have actually outsourced this to companies who provide consultative bidder platforms. And the average number of what it costs to build and maintain a bidder is about $5 million a year. That assumes that you're going to keep up with all the latest protocols, that you're going to actually try to bid on every impression. And that's really $5 million that you invest before you actually do anything unique or interesting. This is just to get into the game. This is your ante for those of you who like to gamble. And it doesn't really matter what happens next. You've already spent $5 million every single year building this technology. I believe, as I think many of you do from conversations we've had in the past, that the real value comes not in can you build a bidder, but what does your bidder do? And really, it's not the bidder that does it, it's the algorithms that you're executing in real time. Just to give you a sense of the scale of this, These are numbers from AppNexus. Right now, we have 4.3 million creatives live in our system. We're running, at any given time, about 1.4 million active campaigns. And on average, we make bidder decisions in about 2 milliseconds across that full spectrum of all those creatives and campaigns. We have 1,500 servers. I can't do the math in my head, but it's well more than 10,000 cores that we're using to execute these real-time bids. And all of that really means, oh, it says, I could have just read the next line. Who changed those slides? That's the number. Real-time reading. The question becomes, can we use this incredible computational heft for the benefit of clients who wanted to run their own algorithms? Raise your hand if you've called AppNexus in the past 5 years and said, can I run my algorithm on your bidders? Or improve, segment modifier or something else? It's a pretty good number of you. I know because you always call me. And my answer is always no, it's too hard. And I always thought it was impossible, like actually impossible, because we can't really have your code running on our servers and crashing them. That's bad for everybody else. And how can we constrain the amount of CPU you use? If you write an algorithm that goes amok, not that any of you ever would run something amok, right? If you've asked for object limit increases recently, you went amok, all right? How can we ever let you into this incredibly finely tuned system? Impossible. Until I met Paul. And Paul said, well, why don't you just use wavelet trees? And I said, great question. Totally thought of that. And then I walked away really fast, went to Wikipedia and looked at wavelet trees. They're not even in there. So is he messing with me? I always have that question. Am I getting old? Are these people messing with me? I don't know. But, I said, Paul, well, if you think wavelet trees are going to work, why don't you just go build it, And sort of laughed to myself, he'll never come back. And then a couple months later, he was back. And he said, this is actually possible. I've talked to a bunch of my colleagues. I'm kind of afraid to ask who these colleagues are. You get the picture in your head. And they said, look, there's all these techniques we can do to actually make this something we can execute in real time. And so in just a second, I'll bring up Paul to talk about exactly how we do this. But let me give you a quick sense of what we've done, which is, just to help Pat out, we've created the AppNexus programmable bidder. It's a little bit more sophisticated than a surge protector, but it does allow you to plug in your own algorithm into our systems. And we can actually execute your own custom logic in real time on every single ad that we see. This means no timeouts, it means no scalability issues, and maybe more important, it means that you don't have to build all the supporting infrastructure. You don't have to worry about reporting. You don't have to worry about UIs, UX, nothing. All the things that you get from our platform every day as part of the deal, you get with this, except it's now running your logic. If you tie this to what Riley talked about this morning with the real-time streaming data, what you have is a system that can take real-time data input, either through our cookie monsters or through your own real-time data provider, that can spit out real-time reports through our Pulse that we announced last year, that can do real-time trafficking, so any changes you make to campaigns go live within 5 or 10 minutes, and now can run real-time algorithms in a matter of a couple milliseconds. This is truly the first ever real-time platform. We believe this will drop the cost of running and building brand new algorithms, custom algorithms, dramatically to next to nothing in comparison to that $5 million. And we think this will unlock more innovation and creativity than we've seen in this industry in a long time. Because today the barrier of entry to go do something really interesting is building a bidder. And now it's not. So with that, Dr. Paul Huang, here to talk about just what is a wavelet tree.
So when I first started this project, the first thing I said was, all right, you want a decision tree, you don't actually know what you want, Brian. Let's just end up do a Python, something else standard, and then you guys can play around with it, and once you figure out what you actually need to have in the bidder, I can implement it for real and see. And Brian's immediate reaction was a strong, very typical Brian, no, I don't want a toy, I want something that scales right now because I know what I'm doing. So I had to go back to my whiteboard and kind of figure out what the challenges are and how to address them. And So this was touched upon earlier. And one of the big challenges with loading someone else's code in your bidder is you have to make sure there's security. We all know ActiveX worked very well for Microsoft. We kind of want to do better. You need isolation between members. You don't want one member's campaign to kind of stomp up over another member's settings, that sort of thing. And you want resource control. Just in order to keep costs reasonable, you want to make sure that not one member can use up too much memory or too many CPU cycles per option, and then everyone loses. And then talk some more about it. And the problem with running code on 1,000 machines is that you can't debug it. And you can't debug it if you have to go through an account manager that will contact me. And then I will look at crash dumps on my box and have to soup. It's just not doable. We need some sort of static analysis that we know that once code is in the bidder, it will not crash, and it will just do exactly what you expect it to do. And finally, we need performance. If we want to do this at scale, so that every single object in a bidder can have a decision tree, we need very good performance. So this is the timescale we work at. The RTB phase, the real-time bidding phase on the AppNexus bidder is about 1 to 1.5 milliseconds. And during that time, we'll look at on the order of 2,000 campaigns. So this is a lot less than the initial 1.4 million active campaigns. There's an earlier phase that does very aggressive pre-filtering there and brings it down to less than 0.1% of the total. And finally, when we look at the distribution of time per campaign that we look at, we see that we spend about 1,000 to 2,000 cycles per campaign on average. And I haven't graphed it in a while, but it looks usually like a bunch of campaigns, say 80% are very quick because we don't actually bid. So after 500 cycles, we can say, all right, no, we're not buying anything here. And the real decisioning end-to-end takes under perhaps 5,000 to 10,000 cycles. So just as a scale back to seconds, we run on about 2.4 gigahertz machines, so 1,000 to 2,000 cycles is about 0.5 to 1 microsecond. And another thing that Brian brought up was, why don't we just run native code on the bidder? And my answer kind of surprised him, I think. It was, the problem with native code is it doesn't scale. So what do I mean by it doesn't scale? This is a graph of what happens to your instruction per cycle, IPC, as a working set size of the total executable grows, and as a factor of the basic log size, so about how many instructions you execute before you jump around to something else. And what we see is at the top left, this is micro benchmark land. All your code is in L1, so level 1 cache, so you have exactly 32 kilobytes of code, and everything runs amazingly quick. In the real world, you usually have perhaps on the order of 100 kilobytes of really code on the hot path. For instance, AppNexus bidder has 2.4 megabytes of executable, and perhaps 10% of that goes on the hot path for bidding. So we see we're about on this region after or before the second bump. Where it's written bidder, we see in prod about 1.2 IPC for real. And so this means that for every single clock cycle, we execute about 1.3 instructions on CPUs. And then we see what happens when we don't have enough level 3 cache for the instructions. So when we have more than 16 megabytes of executable code, then everything goes to not very good. So for instance, we see what used to be the 1.2 IPC for bidder is now 0.25 to not 0.5 perhaps IPC. So now, whereas before we had a 2.2 gigahertz machine that executed about 1.2 instructions per cycle, so about 2.6 gigahertz in terms of instructions. Now we're down to, 700 megahertz in terms of instructions per second. I don't know the last time you guys had to work with a 700 megahertz machine. I know for me that was in high school. Unreal Tournament was awesome at the time, but that is not the way to scale. We just can't run that much native code without basically screwing up performance for everyone. And there are two reasons for that drop in performance. The first one is simply throughput. As you go from level 1 cache that has very good bandwidth, I think it's 32 bytes a cycle, something insane like that. And he goes down to level 2, level 3, which is still pretty good, right? It gets up to 3.5-ish IPC in theory, so this would actually be bytes per cycle. And then you hit main memory, where we see the bottleneck is 1.4 bytes per cycle on my machine. You may be thinking, I get much better bandwidth than 1.4 bytes per cycle on my machines. The reason for that is that when you do data, you have multiple data streams usually. You might have multiple threads, and all of these kind of multiply, so you get 1.5 bytes per cycle per stream, per core, that sort of thing. But if you're executing instructions, you only have one instruction stream per core. And the other reason is the fixed cost on random accesses. At the bottom, it's just, well, just bubbles in the pipeline and that branch predictions. But the real problem here is at the end, when you hit main memory, and you have to deal with the TL mimesis, so just translating virtual addresses to physical addresses, that will tend to have easily 100 cycles to your first memory access, and then random access to DRAMs is much slower than streaming accesses. So that's another, just the first jump will cost you on the order of 350 cycles. So basically, we can't do that. If we look at just a very simple decision tree, that would be perhaps the initial transfer to jump into that decision tree would be 350 cycles. So let's say it's only 1 kilobyte of code, and that's really not a lot. If you look at native code, that would be just loading that into memory would be 700 cycles. And let's say you have 2 conditional jumps, because that's why we're here. We're trying to modify the bits based on dynamic information. That would be perhaps another 500 cycles just because of the random memory accesses. So total here, we get to a lower bound of 1,500 cycles for a fairly small decision tree. So at 2.2 gigahertz, that's 0.7 microseconds, which is very close to our average end-to-end time when we looked at a campaign. I also know some colleagues who do this in the real world at a DXP, shall remain unnamed. And so I asked them, right, my initial estimate here is that I have a lower bound at 1,500 cycles or 0.7 micros. I'm guessing it's probably a lot worse in the real life. So let's say it's around 4-ish microseconds per decision tree with something realistic. And I never got an answer. I did take a look, however, and that look said, I wish it took only 4 microseconds to execute the decision tree in native code. So that's what I had. I knew basically what could not work. You can't embed a normal language because it's going to be too slow, it's going to be hard to analyze, and you can't just compile something that you know to native code because native code doesn't scale. And then I started thinking about it over lunch. I ran into Maria, who's an engineer on the Dirt team with Riley, and she said something like, I love languages, I like parsers. So first reaction is, you're weird. And second is, I have a perfect project for you, please help me fix this. So Maria?
Hey, what's up everyone? So, as Paul was saying, native code won't work for performance reasons, but he didn't even touch on all the reasons why it also wouldn't work for all of the other problems we talked about. And what those basically boil down to is we want to protect everyone. We want to protect ourselves from anybody executing some weird or dangerous stuff on our platform. And we want to protect you, the clients, from potentially shooting yourselves in the foot from passing in some bad logic into a bidder that's like suddenly off in production and bidding on all of these things. So we were thinking about ways to sort of decouple a solution for that problem from the performance problem, and came up with this, creating a domain-specific language for decision trees to be inputted into the system. So how do you make a language for decision trees? First, we can take a look at what decision trees in this context actually look like. This is an example of a decision tree, a pretty simple one, for a bid request coming in. In this case, if the bid request comes in and user is in segment 1, 2, 3, 4, we traverse down the yes path to check whether the domain is theguardian.com. If so, we traverse again down the yes path and evaluate what hour the request is coming in. And basically, for every possible evaluation of these paths, we arrive at a leaf node that is a price that we will bid for the impression. So some of our goals in designing a language to represent these decision trees come from a lot of the problems we're trying to solve. Like Paul mentioned, static error checking is really, really, really important because we want to make sure that these trees are valid things that will do the correct thing once they get into production. So it's important to be able to have very clear type definition for this language. We want to have super precise and exact error messages. If we're using like really big machine-generated trees, we don't want to tell you, oh, there's an error in your syntax around line, 18,004. We want to be able to point to the exact token where things went wrong so you can fix it pretty easily. We want to have a good way to bound execution time and memory usage. This is just sort of the general problem the language solves because we can bound on text size, we can also bound on the number of nodes that a tree is, and have a fairly good way to make sure that we're not passing in anything that will really blow up our systems. High performance implementation. So we wanted to make sure that rather than building this super expressive language that lets you build out all sorts of really complex logical things, we want to make sure first and foremost that we can implement these semantics efficiently. So we went for sort of simple logical constructs that you can still build pretty robust trees with, but that we know we can implement very solidly on the whole side of things. And finally, as a sort of side goal, we just wanted to have a human-readable tree. In the event you're making smaller, handcrafted trees, it's helpful to be able to just look at it at a glance and have an understanding of what the logic will be, as opposed to a more confusing setup. So with all of that in mind, came up with Bonsai, a language for building trees. So here's an example of how you would construct a bonsai tree for the decision tree we just saw. You'll notice it's very Pythonic. We use whitespace to sort of indicate blocks of meaningful code. In this case, rather than being a Python program, a bonsai tree is just a series of chained if or else statements. And the parser will validate that every possible evaluation of this tree has a node. So in other words, every if block will have to have a matching else. So take a look at this example. It's pretty straightforward. If you just read down, we check if users is stay with 1, 2, 3, 4. Check if the mate's a guardian. We check if hour is in this range, and if so, we return that value, and we just sort of traverse down the path that way. So these are the constructs we have initially implemented in the language. We have switch statements, which are super helpful if you want to have a bunch of different leaf nodes for a certain feature in the tree. By feature, I mean like domain, hour, the things that we saw before. We have Boolean expressions. They're implemented using any and every keyword as opposed to and or not. Paul will discuss the technical reasons for that decision later. We have a range operator for ranges of numeric values. We have a list operator for checking if a value is in a list of possible values. Equality, inequality operators, and negation, so your basic value testing operations. And because these are the supported features currently implemented, we'll continue to build out more to finally arrive at full parity with everything that's available for campaign evaluation. So looking at a couple more examples of some of the features and syntax constructs we just discussed, here's another sort of simple one. It's checking whether cookie age is less than 120 minutes. And if so, here's an example of the Boolean expression. So if any user day equals 6 or carrier equals Verizon, means that if user day is Saturday or if the carrier is Verizon, go down to that node. Otherwise, we check if user day is 7, and if not, we finally arrive at the final else statement. Here's an example of a switch statement. In order to make sure that every path has a leaf node, we need to include a default case in this case. But otherwise, it's pretty straightforward. We just check and see whether a country matches any of the values in the first one. If so, we go down to 0.15 and start to just evaluate the same way. And you'll see here also an example of the in operator, checking if URL is in that set of URLs. So yeah, that's kind kind of overview of what the input into the system looks like. And we'll bring back Dr. Paul to talk more about wavelet trees and where they actually go.
Right, so as Maria mentioned, one of the special things about the DSL, the domain-specific language, is that you can't have arbitrarily nested Boolean expressions. You only have one level of conjunction or disjunction. And there's what I think is very good technical reasons for that. So the basic model for decision trees doesn't allow for any of these. If you want to say, I want to do this if A or B is true, with decision trees, you kind of have to duplicate the subtree and say, if A is true, do this. If B is true, do this again, but you have to copy paste all of that and then duplicate that structure in the in-memory representation as well. And it's not ideal. So what we do here is that instead of compiling directly to a branching program, we compile it to a non-deterministic branching program. And by non-deterministic, we mean that each node will have a false or a true child, or perhaps both. And it can also have a don't care child. And what happens during evaluation is that conceptually, we always go down either the true or false branch, depending on the value of the test. And if there is a don't care branch, we'll also go down that branch. So for instance here, let's say W is true, then we'll visit the subject test for X and finally may output A. And it will also take the don't care branch and test for Y, Z, and then return perhaps C or B. So because this is non-deterministic, we may have multiple outputs. Now we also have zero output, but at construction that will never happen. And the trick here is that because we only allow one level of nesting in or and statements, or expressions actually, we can impose a total order on the leaves and disambiguate by taking the minimum leaf. So for example here, the total order is simply left to right. Because let's say B is reachable. If A is also reachable, then that's because W and X are true, therefore the result should be A and not B. However, if A is not reachable, then we can look at either B or C. So that's the first thing that gives us, I think, a lot more power than classical branching programs or decision trees. And then the other thing that makes it useful is that we actually execute these decision trees efficiently. So what we do to kind of take a decision tree and make it more efficient to execute is that first we flatten the tree. So we say for each output node, for each leaf, what are the conditions that must be true or false so that that node is reachable for the root. And once we have that, we can build a bunch of reverse indices per feature and say, let's say country is the United Kingdom. What are the leaves that may be reachable given that information? So that would be enough to execute these. We could basically take the reverse indices for all the features that we need to look at and take the intersection of the leaves that are reachable. The problem with that strategy is that there's a space blow-up, right? If you have one test that happens at the top, it will be duplicated to all the leaves that are under that subtree. So the nice thing about the structure is that the reverse indices are highly compressible because, again, if we have a test that happens at the top, then all the subtrees will also have that test. So we, instead of saying, if country is the UK, then node A is reachable. If country is the UK, node B is reachable, etc. We can see if country is the UK, then nodes A to Z or whatever are reachable. And that gives you back linear space usage. So that's very important, because as you need to scale, the bottleneck becomes the speed of memory accesses. So if you have something that's more compact, then it'll be quicker on average. We'll also get back streaming memory accesses, because instead of having to traverse the tree, we can search reverse indices that are highly optimized. And finally, we don't have any serial bottleneck, again, because we don't actually traverse the tree. What we do is we search reverse indices, and that can happen in parallel, and at the end, we take the intersection and do one disambiguation pass. So how does it work? Well, first, as I said, the most important thing for us is memory usage and making sure that these decision trees scale down as well as up. And the reason for that is that, I can tell we don't have no usage data, but I feel like most people would start small with, say, decision trees that have 4, 5 output leaves. As they get more comfortable with the system, they will then grow this and perhaps even start generating them with computers. So we want to make sure that we support very well that use case of having small decision trees and small tweaks on otherwise classical campaigns. So the minimal tree here, this is 128 bytes. I feel pretty comfortable with that figure. That's 2 dash lines. Yeah, all right, cool. So a small tree, that's something that we built by hand. That seemed representative. I think it branched on geo and segment information. That was 256 bytes. So if you don't have a big tree, you don't have to pay for a lot of overhead. And finally, there was this, so data science was our first internal customer. They came up with something that had 212 leaves, I think, and something like a couple thousand targeting statements in there. So that took 88 kilobytes. And I know it seems daunting, but then I realized to have the same effect, to re-implement the same logic in our current system, they would have to create 212 campaigns. So this is actually a huge memory reduction versus what you might have to do to realize the same impact if you don't have the flexibility of decision trees. So runtime here. It also have the same pay-as-you-go effect here in that you don't spend a lot of time working on small trees, but you still have something decent for very large decision trees. So the first call into the logic for decision trees took 3,500 cycles. So that's the example of what happens when you try to execute code that's not in cache. You end up just waiting for memory all the time. The minimal tree, so that's the base overhead of our system, that was 600 cycles. The hand-rolled tree was 1,500 cycles, which it seems pretty reasonable. That's about twice the amount of time that we spend currently in campaigns. So hopefully if you're using these decision trees, you're going to bid more, or at least better, with better targeted prices. So that's more spend for everyone, more revenue for some of us. And there's also the large tree, which took 20,000 cycles. Again, that seems large. That's 10 microseconds. That's about the amount of time that we take end-to-end for a campaign that bids, to select a creative and all of that. But again, you have to compare that to what it would take without decision trees, and that would be 200 and some campaigns. That would definitely be more than 10 microseconds. So I feel like we have a system that scales well, but one of the reasons that the tree is so large is that we don't have the features that data science needs. And that's part of the conversation I want to start here, is I want to understand what people need to build the logic so that we can say that it's doable on our end, and that way they have something that's expressive and that is easy to use for everyone. So I can now introduce my guinea pig / taskmaster, Abe from data science, who did all the work of creating our first machine-generated decision tree.
I actually didn't do all the work. Our data science team did all the work. I just asked Paul for more things, and then I asked the data science team for more things to use the things that Paul built. But we're very excited about this because, Brian and the engineers came to us. They said, hey, you can program the bidder. You can now pretty much bid what you want, where you want. So go bid what you want. And data science, we thought, that's great. Let's have a machine tell us what to bid. So we made machine-generated trees. The basic idea is the first test was that we would do a predict to a CPA buying strategy. So we would use a tree to calculate the probability of a conversion, times it by a goal, attach it to a campaign, and start bidding. So we chose classification and regression trees. Very classical tree technique. It's used a lot in medical diagnosis and other applications to build the tree. Now, to give an example of what a cart tree looks like and how it works, we have, say, you're in a room full of Americans and you want to identify a British person, or at least get the probability someone's British. Now, if there's 10,000 people and 400 Brits, you could say, okay, there's a 4% chance. Or you could do better by asking yes or no questions and then making a new guess. So, for example, if this person says sorry for no reason a lot, well, the chance that they're British drops from 4% to about 1% in this example. And you say, okay, are they awkward when hugged? Do they think me as an American are too friendly and affectionate? Well, yes. Now, they might not be British, they might just be an engineer. We're awkward people. But it still increases the chance they're British. And then finally, we asked the question here, do they like to queue in an orderly manner, like a nice line for the bus? Yes, at this point, we're saying, okay, there's only 400 Brits in the room out of 10,000 people, but knowing what we know, we're just going to make a guess, 50% chance they're British. So, elaborate extended analogy, as you guys know, for us it's impressions and conversions. People are impressions and British people are conversions. Don't know how that gels. So what we did is we used a card algorithm to make a giant, as Paul pointed out, machine-generated tree where we use a lot of different predictors: advertiser recency, frequency, URL, geo-region, device type, supply type, OS family, hour of day, day of week. I'm sure there's things I'm forgetting. And we grew a tree. It's in production right now. It's buying right now, which is very exciting because it works. It's this big thing. It's attached to a campaign buying real ads with real money. Now what we really like about the process, though, is it's very easy for us to automate the tree building. Easy is relative, and I guess a relative term, but it's easy to update your model and get it in and out. What we really do is we have scripts to pull the log level data. You know, you as users can pull the data. I don't know what feeds you use, however you get your data. We've automated our tree building process. We use Apache Spark to build these giant trees. We wrote scripts that take the tree object in Spark and then parse it to the Bonsai language. And then once we have the output in the Bonsai language, we load it to the API and we're done. And right now it's bidding. Then later on, you could wait a day, wait an hour, wait whatever you want, pull more data again, iterate and repeat the process. It's hard to say how much time it would take the whole thing. It's the second box for us that was very time consuming. You know, that's really where your expertise comes in and how am I going to buy ads. But at least the act of pulling the data, inputting it, and using it is pretty easy. So, you know, again, for us, data science, it's great. We threw a bunch of features in the past. If we wanted to test something, all of a sudden we had to go to the bidder team, you know, and beg for their time-consuming work to touch this very sensitive, expensive system, and now we don't have to do that. My arrow. That's it. Brian's going to close us out.
All right, so as you've just seen, we did the impossible. I know most of you followed most of what Paul said. There will be a small quiz later. Do not try to implement this at home, is my personal advice. So what we have now is a powerful system that will allow you to, right now, start to build bonsai trees, upload them into our real-time production infrastructure, and use them to, hopefully, invent, create, improve, and generally, shall I say, optimize, which is, of course, what inspired the name of today's event. So, thank you. Awesome job. Thank you, Maria. Thank you, Paul. Thank you, Abe. And thanks all of you in advance for playing with this and helping us make it something that's truly valuable for all of us.